dimensional data and homology?
Yeah, so I absolutely welcome questions. I'm going to go at a very uneven pace because I'm assuming that there are parts of what I'm talking about that people are not familiar with and parts that people are familiar with. And so if I've got my assumptions wrong, feel free to interrupt, to speed me up, or most importantly, to slow me down. All right, so, okay, so that's the title. Oh, there, all right, different. Okay, so let me start with data, and I'm going to kind of artificially assume that there are two forms of data sets. This distinction is very useful for the way I'm going to present it, but it is a bit artificial. And so the idea is that one way that we get data is in terms of point clouds, and I'll try to make it clear what I mean by that. And the other way is in terms of scalar fields. You could think more generally in terms of vector fields, but let's keep it simple for today and just talk about scalar fields. So what are point clouds? And I'll give you an example of a point cloud. I'm going to give it to you in the context of a particular map, which is completely irrelevant. I mean, in some senses, a red herring. I'll make a point with this, and I will return to this, at least the pictures from this, the very end of the talk. All right. So this is kind of the long-term goal of what I'm talking about. What is an infinite dimensional map? Have a function. Let's see, somehow, whoops, I've lost. Do I have? Okay. So if you see psi, what you should think of it as psi being a function defined on the interval minus pi to pi. And what this can be presented, and it does in this Koch-Shaffer model, is a density of, for example, plants. And on the right-hand side of that equality, one sees inside the integral a quadratic function of psi. You have psi times 1 minus psi divided by c. But that might remind you of the logarithmic growth function. Think of plants growing. They have to compete with each other. If they're too crowded, then they don't grow as well, and that's kind of what this logarithmic growth function represents. Would be kind of the intrinsic growth rate. The summer comes along, the plants produce seeds. The seeds then get blown around the domain, which is this interval minus pi, in some way that's described by this dispersal kernel that's given by D. So from here to the next, you get a move from one density function to another density function, and this is a dynamics. This dynamic system, it's n-dimensional, so the typical way to do that is via numerics. One is to take, and if we assume functions are periodic on the domain, use Fourier series to decompose psi. Get an infinite set of maps that Fourier coefficients map to themselves. Of course, we can't work with this infinite map, so we take a finite set of Fourier coefficients. By linear projection, you just ignore the higher order terms, and that's called the Galerkin projection. And we did a simulation with 50 Fourier modes. And we're looking at is a plot of, I think, 50,000 points. So this is a single trajectory. Plots looks at the first and second Fourier coefficient against the second Fourier coefficient, and the other plot looks at the second coefficient against the third coefficient. For systems, this looks kind of like a chaotic dynamical system, and what can one do with it? And the reason I raise this is because one can use logical methods. It needs the estimates of, the errors that one's making by the numerical methods, the error one makes by the Galerkin projection, so one has to do some analysis ahead of time. But one can then use purely topological methods, which I'm not really going to talk about during this presentation, to really rigorously conclude that this does exhibit chaotic dynamics. For those who know what it means, what one says is that there is a subshift dynamics with where the log of the eigenvalue is positive. So, rigorous proof, but the idea that I would like to get across at this point is that in essence, one needs this cloud worth of data. So, what you should think of is that you have points. We did the simulations in 50 dimensions, but we actually did the proof using the function into, depending on the part of the proof we did, 6 dimensions to 12 dimensions. All right, so it's a point that's obtained by taking initializing it for 3,000 time steps, and one was able to make about the dynamics. Well, we could rigor because I started with an exact nonlinearity and I could do all the estimates, but one imagine that if one had actually sampling some process, that one might see some similar kind of point cloud, and we could ask, well, is it possible to use topological data methods to get a description of rather complicated dynamics? And my hope is that if one day we'll be able to, yes, it's there yet. Let me talk for the moment. I'll come back to, I have put that example up at the very end. Like I said, let me, for the moment, switch to a different type of data set, which I think of as scalar fields. I don't want examples. So the one is Rayleigh-Bernard convection. So this, well, what we're looking at is actually a small, the real size of this is about the size of a nickel, the thickness of your thumbnail. And this is a shadow graph that's coming from Mike Schatz's lab at Georgia Tech. And it's actually CO2 inside that's being heated. And light is being shown on this image of this experimental device. It reflects off the back, and that is the image. It's a movie. This is what happens in time as the camera is catching what's going on. You should think of is that the dark regions, and which is light and which is dark, but think of the dark regions as representing where the CO2 is cold, the light regions representing where the CO2 is hot. Remember, in a convection experiment, Rayleigh-Bernard convection experiments, you're heating from the bottom and cooling from the top. So there's a fairly complicated pattern that constantly is changing in time. Right? Think of the grayscale image that you're looking at as being an approximation for a temperature field, being a single number, and so we have a scalar field. This is now coming from a numerical simulation. The other, the convection was experimental data. This is numerical data, again generated by Mike and collaborators at Georgia Tech. This is a Kolmogorov flow. This is a J model for turbulent. And again, what you're looking at here, I think, is a vorticity field, a scalar field. It's plotted very nicely in MATLAB, so you get nice colors. But on the right-hand side, you see the vorticity bar going from -3 to roughly. So once again, we have a scalar field. And watch this go by, you might stop and think, what kind of dynamics am I seeing? Okay, so simulations of complex systems, very complicated scalar fields. I understand the dynamics associated with this nonlinear PDE. Can use topological methods to do that. Here's something different. It's coming from Bob Behringer's lab. What you're looking at there, you can see that there are lots of little disks. Those are photoelastic disks. There's light being shown through photoelastic disks, and the photoelasticity means that when you compress the disks, you get nice diffraction patterns. This is where you see a lot of the colors, and that indication that the bead is being compressed. It becomes an inverse problem to look at each bead, to look at the color rings on the bead, and to decide exactly how much force is being put on these bead disks. I really should be saying rather than beads. So that's what Bob Behringer's group does. They take these pictures, then they solve the inverse problems, and so what they're able to tell us at this instant in time is what are all the forces between these disks. And see, some of the disks have lots of force on them, and some of the disks are completely uncolored, and that's because there's really no force on them. Right? So that's the cool thing about what you expect the structure of all these grains to be. If I turn this into a dynamic, or somewhat dynamic, this is really quasi-static. So you're looking at a series of experiments. What group is doing is taking a region like what you saw in the previous one. It gets sheared while volume of this region remains the same. And it gets sheared one way, and then it gets sheared back, gets sheared one way, gets sheared back. And what you're seeing is the action of these force networks through the shearing process. So quasi-static in the sense that shear, you stop, you take the picture, you reverse shear, you take picture. So it's not dynamic because you're stopping each time to take the picture. But what one does see is a clear evolution of the structure of the force network. And what, of course, I'd like to be able to do is give some simpler description of what kind of dynamics is taking place, what kind of dynamics one would expect to see. And so what I'm doing as we're doing this is that there's really a tremendous amount of data being presented in front of you. Now, this data is somewhat tedious, but back to Mike's convection example, once you get the convection experiment running, it runs on its own, and you just have a camera there, so it's very easy to get complicated time series. Here's another example. I have any work on this, but it's just such cool pictures that I thought I would show the movie. So again, you have these beads, and here a large object has been dropped on beads, and how these force chains produce really cool patterns. Again, what to do is to have some coherent description of what's going on there. All right. Simulations. So what you're looking at are simulations done by Lou Kondick's group, where what happens is that you have a box filled with these particles, and you just compress the boxes uniformly from the sides very slowly. And these were actually two different systems. Both the systems involve particles of the same size. The one left involves static friction, and the one on the right had kinematic friction. So this is numerical simulation. It it looked like maybe there were some differences in how it progressed. I looked at the color, which is an indication of the forces on the particles. Either one on the left is slightly different from the one on the right. We would like to be able to quantify these differences. So, you know, lots of different directions one can go with these kinds of problems. I'd like to talk about one that we're working on right now, and that is it's a project that I have with Mike Schatz and Mark Paul. Mike, again, is at Georgia Tech, and Mark is at Virginia Tech. So you have this experiment, this Rayleigh-Bernard convection experiment that's taking place. Here in MATLAB rendering the image that's a higher resolution than the one that I showed you earlier. Data. Numerical simulations. This comes out of Mark Paul's lab. These are very large-scale 3D simulations. In order to somehow match the 3D numerical simulations to experimental data, what Mark just shows us is the mid-plane. Two-dimensional slice of a full three-dimensional computation that's being done, because it's all that we can get out of Mike's. And the question is, are we, from the experiments, seeing the same thing that the numerics predicts, or vice versa, is the numerics doing a good job of predicting what the experiment is doing? All that. Well, one way is to say, look, the fluids problem, maybe we can get Stokes to model it. I think everyone would accept that Navier-Stokes is a reasonable model for this. Still, even on that level, there's some subtleties. The fact is that there are boundary conditions. You have to choose the walls, the top, bottom plates, and what walls or how you put the top plate. The top plate we want to shine a light through, so that puts some restrictions on what we can put on the top plate. Bottom plate, it has to be heating, and it's supposed to be reflective. So again, put some constraints on what's going on. Those are, I again know that much about fluids, but my impression is that coming up with accurate representations of the boundary conditions that go into the numerical model is a non-trivial task. It's not something that you just have a nice simple equation like Navier-Stokes that can be written down. In addition, for problems like this, Navier-Stokes is quite difficult to solve on. It's known to be a difficult set of different partial differential equations to solve. So one likes to solve an easier equation, and there's an approximation to the Navier-Stokes equation called the Boussinesq equation, typically used for these kinds of convection experiments. In this situation where we have maybe an idealized mathematical model that we might think of as being established truth, in practice, when we do numerics and we want to compare them with the experiment, we're not going to use the full equations, these boundary conditions, which, you know, we're not quite sure exactly how they should be put in. Right? So, question is, compare the results. We saw the kinds of image coming out. I'm going to show you much simpler images, which is where we're at now. But you see that you had a very, very complicated pattern. People would, I think that this represents spatial temporal chaos. And so any slight deviation in the initial conditions means that eventually the patterns will look very different. So how do we or not the experimental data and the numerical simulations should match? Obviously, it becomes somewhat of a statistics question, but still we need to be able to go from pictures to statistics. Very topology will come into play. Okay. The way I did it is that we're observing patterns of a density function or a temperature function, and so what we're interested in is quantifying the shape of the function. So to do this, of course, this is the applied algebraic topology network. We use algebraic topology, and I want to start with a very simple measure using homology. All right. So there's my experimental data. The thing one has that, the black regions represent the cold fluid, so that's where the fluid comes down. The white regions represent the hot fluid, so that's where the fluid is coming up. You have to have conservation of fluid, so there should be as much fluid coming up as going down. The assumption is that if I look at the median grayscale, then that everything above that should represent everything above it should represent upflow. A very natural way to threshold this image. So what we did was for every frame, we can the median grayscale and we threshold. Right? The dark became black and the light became white. And now I have two sets. I have a black set of pixels and I have a white set of pixels. And two, I think in this case I'm looking at the black set of pixels. I can count the number of components of the black pixels, which I've colored just so it makes it easy for you to see which the components. And of course, that's exactly what Betty 0 will tell us. 34 components here. Again, looking at the loops that the black pixels make, and I've highlighted them in red, and so there are 14 of these loops. Now, exactly the same count for the white pixels. Conditions, so there is no duality that exchanges these directly. So therefore, what I'm saying is that if you give me an experimental data image, then I'm going to associate to it 4 positive, 4 non-negative integers, beta of black, beta 0 of white, beta 1 of black, beta 1 of white. And 1,000 of those 4 vectors. What I do is just say, well, what's the probability of any one 4 vector happening to determine an entropy? And we did this. So this was done with Tilda and Mike Schatz. And I'm now a proposal for a way to measure the complexity of this non-dynamic system. There are more standard ways that the physics community has done using this Carhu-and-Lou decomposition, which you can think of as basically doing a spectral analysis and seeing what action of the spectrum is activated by the system. And that on the left, you get a sense of the entropy as a function of using the rotational homology. On the right, you see what could be done using this more standard linear analysis, and you get a nice match. Made numbers, but in terms of slopes and growth rates. What's important, however, is that to do linear analysis, to use the Carnot-Lou decomposition, is actually very difficult. That's very, very high dimensional computation. In order to be able to do it, we had to make use of the fact that there's an S1 symmetry of this disk. We actually measured, measured the patterns on that circle, used the Fourier analysis on that circle. So if with a non-symmetric region, I would not know with complexity going on, I would not know how to actually perform the computations given the computational tools at my disposal. So, situation where very, very simple topological ideas can reach the kinds of results that one sees using more techniques, but at much less cost. Or we can do very simply with homology as a way of using or quantifying patterns. What I got here is a little bit closer to this question that I asked. You know, how do you do comparisons between numerical models, theoretical models, numerical get from them, and what you're seeing experimentally? So one of the reasons the Boussinesq equation is simpler to solve than Navier-Stokes is it has extra symmetry in it. So solutions to the Boussinesq equation should exhibit an up-down symmetry to the convection problem. And what you see in these pictures are the Betti numbers. So in the left graph, you see the dot is the beta 0 for the cold fluid, and the black pixels, and the white is the beta 0 for the hot fluid, the fluid that's coming up, the white pixels. And what we see is that they don't agree. So this really says that there is a lack of up-down symmetry. You get this lack of symmetry grows as you move to the right. There's some measurement, there's some quantity Q that's there. The Boussin number is basically a parameter. And my understanding is, depending on scaling, and I think for this particular problem, the scaling has it at 1, that 1 becomes a bifurcation point, and once the number crosses 1, then this up-down symmetry is broken. So, not surprising, one sees that you move from left to right, that this is broken. That's what you would expect. But again, there is a parameter, and the break symmetry is a local bifurcation. Away from that bifurcation point, the linear can no longer tell you just how divergent you are going to be, how far away you are from the up-down symmetry. Logical methods would provide some kind of quantification. And remember, the model is never expected to exactly reproduce the results. One model is reproducibility within a certain constraint and certain tolerance, providing the user with some information about just how much tolerance, in this case with regard to the up-down symmetry, is lost in the nonlinear regime. It's quite possible that this amount of lack of symmetry is acceptable for a particular application, in which case one would be perfectly happy to use the Boussinesq equations for simulating. On the other hand, if up-down symmetry is something that's very important, then it suggests that you have to give up using the Boussinesq equations and move to a more complicated set of equations to solve much earlier. So mind you, what we did here was something really very simple. There's a threshold. We set that natural level, and then we use homology on the two patterns to extract information. And, I've got some interesting stuff of that. But of course, for more general problems, there's no reason that there should be this natural threshold. Any single level should characterize shape of a function. So, well, it leads us into persistent homology. Again, I want to now think about this as a scalar field. Field, what I'm going to look at is super level sets. So I'm going to look at the X in the domain where, given the scalar field, the value of F is within a particular threshold. The Betty numbers associated with that. And here I'm going to go because I'm assuming most people are familiar with persistent homology. Limits to the Betty number. So here are two graphs where if I count the Betty numbers at any threshold, they look exactly the same. But I think both of us, all of us would agree that the are quite different. Persistent homology then is to realize that if you change the thresholds, then you get inclusion maps between the domains, and that induces a linear map on homology. And so if at some threshold I see a generator in homology, then I ask, where's the first threshold at which that generator appeared, and where's the last threshold at which it disappeared through my filtration? And if I keep track of those births and deaths, then that is the persistence pair, a persistence point. And length of that tells me how long that generator, with regard to this particular filtration, exists. And if we compute the persistence diagram, where I'm super level set filtration, then it's born at a, if I go through the red figure on the left, it's born at a fairly high level, the first one. The second feature is born at the next level. As I count, I have yet another feature that's born, and that corresponds to the x-axis, the birth axis, and the x-axis. Well, we have this convention that the older always survives. So the first generator that appears is the one that exists for all time. That's why I put it below the x-axis. The generator that appears dies at that lowest hash mark level, and the third generator that appears dies at the very at 0. On the we see the blue curve, and we can do the same thing. We can compute a persistence diagram for it. Persistence diagram looks very different, and so this is a way of distinguishing two functions. All right, but again, I think most people are aware of that. Let me remind you that formally we're going to make the definition of persistence diagram. Give me a scalar field, give me a filtration, and the persistence diagram I'll just think of as a multi-set consisting of one point for each persistence pair, so in plane, and infinitely many copies of points on the diagonal. The reason I do that is because I want to be able to, the reason for the infinite many copies on the diagonal is because I want to be allowed for perturbations. So I have a nice function, a persistence diagram, and I put it slightly with noise. I'll get a different persistence diagram, but the blue points that appeared naturally match to the diagonal because these are noise effects, so their birth and death levels are the same. Again, I know this. Let's actually look at a persistence diagram for, this is coming from the Pomodoro flow. So I'm plotting for you beta 0 and a beta 1 persistence diagram for this. And as we go through this super level set method, you can actually see what the here we've now a lot of components. You might notice that at infinity there's a beta 0 and there are two beta 1s. For that is that this is lying on a torus because the numerical simulations are done with periodic boundary conditions. Because we're using a cubicle of pixelated relation, that's what these points that are sitting on the diagonal are. These really represents holes or consider 1 pixel in size. All right. One is that very different functions can have the same persistence diagram. So these three functions to obtain them, I just rescaled the X and Y variables. So they look very different in terms of being as patterns, but persistence diagrams are identical. Either a plus or a minus. If you're looking at a system where you really don't care about this particular spatial structure, then persistent homology is great. If distinguishing between these spatial structures is really important, then persistent homology is going to be a disaster. Okay. So here I'm showing you again the simulation that was done by Lou's group on the parts that are slowly being compressed together. And to move a little bit more towards the idea of dynamics. Right? For each frame, I can compute one of these persistence diagrams using the superlevel set. And that's what I've done. Blue is the circles correspond to the persistence diagrams on the right. The red ones correspond to the persistence diagram on the left. And if you saw how the red and the blue dots evolved and their final state, see that they're slightly different. And so by tracking the persistence diagrams, in a sense, I'm telling you that the dynamics is a bit different. Now, reduction in information, the reduction in information going from these two that Lou's group produced to be about the persistence diagram, but it's still very high dimensional, and we would really like to be able to quantify this kind of dynamics that's taking place. One of the reasons why it's so important that we have metrics on persistence diagrams, again, I'm assuming that most people are familiar with this. If not, somebody should interrupt. There's the bottleneck distance, which kind of measures the maximal distinction between any two persistence diagrams. The bottleneck distance, which is doing P-type summation over the distances. And of course, there's the fundamental theorem of Konstantin, Edelman, and Haar that says that if you look at the bottleneck distance between two functions, then it's bounded by the L infinity norm of difference of the functions. This is fundamental because it says that if I think of F and G as functions, so I'm in function space and I'm using the L infinity norm in that function space, then map to persistence diagrams is a Lipschitz continuous map. So, that says that this relation that we have is a continuous map. Just like way back at the very beginning when I talked about the Galerkin projections are able to project a continuous map from high-dimensional, infinite dimensional space into a finite dimensional space. And here we have a map that goes from, again, function space, infinite dimensional space, into, well, high dimensional space, and the Lipschitz is still continuous. This is important from a topological perspective. So, the thing that I've said so far is kind of introduction, setting up the problems. I'd like to kind of give you some idea of where we are with regards to moving towards using these topological tools to understand nonlinear systems. So I want to show you very recent work with Lou Kondik and Arnaud Gouillet and Kramer. What we're looking at here is well, of the kind of movies that I showed you from Lou's group. We're doing a compression, and what's being plotted in these graphs is the distance between consecutive persistence diagrams. So these different metrics we have in red the bottleneck distance, in the green we have W1 distance, and in the blue hash we have the W2 distance. A black one that's marked Z is just keeping track of the number of contacts between particles. So for today's talk, it's irrelevant, except that it gives us an idea of when the particles come together. So the idea is we start with a large container, and we now start squeezing the container. the particles move closer and closer together. These particles are allowed to I mean, they're governed by Newton's laws, so when a particle bumps into it, it goes ricocheting away. And that's why it's not so surprising to see that it's fairly spiky in terms of the distances between the persistence diagrams when you have low contacts, when you have low Z. So when the particles are not touching a lot of other particles, they have a room to fly around in this box. And so whenever you have collisions, you would expect that the forces between the particles goes up, and that means getting a change in the geometry of this force landscape, and so things to be bouncing around.
What's the axis? What's the rho again?
Rho is the density. All right, it's a box, and I'm making the box smaller. All right, the density of the particles is going up. It says you replace rho by time if you want. So there are three axes. One is, there's three axes. The one on the right is the z-axis. That's keeping track of the number of tracks between particles. The very left axis is the Wasserstein 1 metric, and then the axis very left is the bottleneck and the W2. Is that okay? Hard to see whether people look confused or not. So, is there any information that we can get from this? What we are seeing is that, think of if Z is large, then the particles, these disks, have lots of contacts around them, so there's not going to be much room for them to move around. And so it's maybe not so surprising that the distance between the geometries of the force networks is changing so much once all the particles have become packed together. What to do is to concentrate here on the ratios between the bottleneck distance and the W1. Remember, the bottleneck distance looks at the single largest feature, whereas the W1 metric, it's like an L1 metric, it just adds up all the differences. And against the bottleneck divided by W2. If B, the 1 and W2 are always going to be bigger than the bottleneck, because the bottleneck is just the single largest feature. And whereas W1 and W2, you're add up all the changes. So expect that the ratio should always be less than 1. What is it on the left part of the graph? This is really large. Well, again, if you think about it, the particles are not much into especially at the beginning, they aren't in very much contact with each other. So collisions that are driving the interactions, changes in the forces between the particles. So those should be happening fairly, and those should be the dominant thing that you see. So say that the major collisions are what we see with, or a major collision is what the bottleneck distance measures, and W1, well, if there aren't many collisions, there aren't many other things to sum up. So, of course, not quite correct, but let's say it just as a heuristic to get you thinking. The fact that dB divided by dW1 is 0.2, what is that there are 5 collisions. So collisions, and they were all of the same size and nothing else than the ratio that you would see. So say when I moved to the other part of the diagram, where the dB divided by D1 is extremely small, and dB divided by W2 is. That's very, very suggestive that once you reach this density, you are seeing very large changes in diagrams in general. Instead, what's happening is that there's lots and lots of very small readjustments in forces between the particles. So from this is that it is possible to just looking at the velocity profiles of the scalar fields to try to draw conclusions about what's happening over these fields. Fluids now, again, one of these frames that I get from my Schatz's lab, we compute the persistence diagram. Here's the B0 persistence diagram. This persistence diagram has lots and lots of points. So analyzing a single persistence diagram is a little complicated. What, of course, in the previous slide was we looked essentially at the velocity. How do the persistence diagrams change? We can say, but of course, if I only tell you how fast someone is moving, you don't get a sense of where they're really going. I mean, they could be driving around in circles very, very fast, so you'd have a high velocity, but not going anywhere. So what we're going to do is we're going to compute the distance between all persistence diagrams. So we've taken 1,000 frames from the movie here, and we've computed the distance between all the persistence diagrams. And if I look at any particular point in there, for example, that tells you what the distance is between the persistence diagram at frame 525 and frame 750. So let's look at these heat maps and try to use the heat maps to try to understand dynamics. So now looking at simulations, and this is from Mark Paul's the mid-plane temperature. And on the left, you see what the simulation tells us, and on the right, you see the persistence diagrams, the distances between the persistence diagrams, the entire frame. And the fact that it has this kind of square, look it down at the one bottleneck on the left, you see are these striped patterns moving off the right. That suggests that we should be seeing periodic patterns in time. And the fact that there are clear squares in there suggests that those patterns change very rapidly. And I think that's what you see on the left. You see something that looks very periodic, but with respect to time, that periodicity is very non-uniform. So persistence diagrams, I can get an idea that maybe I should be, I'm looking at something that eventually, after maybe 150 time frames, settle down into something that seems like somewhat periodic motion, but with regard to time, it has a very non-uniform periodicity. So fast flow dynamics. Once again, here's now experimental data happening because we're in this big blue box in the persistence diagrams. Well, there should be a little bit of chatter now. I know because we kind of see these little blue boxes near the diagonal. And at least with respect to the bottleneck distance, we're getting dramatic change, right? Suddenly we've gone to the orange. So this pattern is the sheet is telling us this pattern is very different from the pattern that we started with at the orbit when we started the experiment. We've seen, again, this little periodic patterns that were in there. I don't know if you noticed at the center, there were little bubbles that form. While comparing the bottom distance to the Wasserstein distance, the heat maps look different. And that's because it's a question of whether we're measuring a single largest change or measuring change over the entire field. Right? Okay. I put together all this data, and next step is to try to do more than just watch these movies or to look at heat maps and say, oh yes, well, that looks like it might be somewhat periodic or not periodic. I'd like to come back and give you more simple descriptors of the dynamics. And so now what I want to do is I want to think about persistent homology in the context of point clouds, talk about two problems. The first problem has to do, both these problems have to do with the fact that, I'm going to use the Kolmogorov flow for this example, has to do with the fact that you do a simulation and avoid having to deal with this problem that it's not quite clear what are the right boundary conditions. Numerical simulation is going to be done on a torus. So the left and the right-hand sides of this image are identified as is the top and bottom. And that's, the movie I showed you earlier. You think about that movie, and hopefully you came to the idea that this might look somewhat periodic. It does, except if you did a Fourier projection of this over, I think this is 1,200, it's not quite periodic, right? Over 1,200 of these cycles, then you see in Fourier space it's really drifting along. So, here R1, this image is the image you see at the beginning of time. After, again, some 100 cycles, you still see something that looks very similar, except it's been translated with respect to the continuous symmetry in the x-axis. If the opposite side of that funnel, I do see a pattern that looks very different. So there is, in some sense, a periodicity, but lost, space, ability to see that this is periodic because you've added symmetries that are unwanted just to be able to do the calculation. If you use the system slightly, they move away from this nice periodic orbit into something that looks much more chaotic. And the question is, okay, if it is chaotic, is there a simpler way to describe the chaotic dynamics than just, oh, it's chaotic? And one idea is that dynamics is really what you see if you have lots and lots of unstable fixed points and unstable periodic orbits. And what happens is that the actual trajectory goes close to, for example, an unstable fixed point, but because the fixed point is unstable, it's going to move away from that. It moves then towards a new unstable fixed point or an unstable periodic orbit, follows that for a while, and then moves away. So that if I understood all the unstable fixed points and all unstable periodic orbits, or at least enough of them, then I could talk to you about this very complicated dynamical system by just telling you what kind of itinerary you expect it to take, or what possible itineraries you could take as involved from one fixed point or periodic orbit to another. What you see in red there are equilibria. How were those equilibria obtained? What was happening was we were on the trajectory. We see where the trajectory slows down. If the trajectory slows down a lot, then it's probably close to an equilibrium point. Take that value, use method to see if there's a fixed point nearby, and identify that. And that's what you see in red. The question is, how many fixed points are there really? Because we know that there are these symmetries in the system. So if there's one fixed point, there has to be at least S1 of the fixed points. I don't want counting circles of fixed points where I think of 2 points on the same circle as being different. I want to distinguish them up to these symmetry classes, all right? So in both cases, what I'd like to do is to be able to ignore the differences arising from continuous symmetry, and of course that's exactly the kind of thing that we think that persistent homology should be able to do a good job at. So to do that, I want to study the set of persistence points, right? Time as a scalar field gives me a point in persistence space, and what I've done now is I have this cloud of points, and in persistence space, it's a nice metric space, so I can form RIPS complexes, which I think everybody here understands, and produce a persistence diagram where the data points are persistence diagrams themselves, right? So there's the persistence diagram, and you know, features that stand out, I think of as being features, all right? So do the clustering of the fixed points. You take your point, each fixed point is a pattern. That pattern is a point in the space of persistence diagrams. And if I look at the beta zero persistence diagram of those persistence diagrams, I can, you know, this is the beta zero diagram. We don't have a firm statement of this, but roughly speaking, anything to the bottom of this blue line is really due to numerical error, and so it suggests that there are 7 distinct fixed points that this trajectory comes close to. If I think about the density part, the first problem I raised, here are the velocity profiles used in metrics. They all are very periodic. So to just look at the space in the space of persistence diagrams, compute that in one, there is this dominant loop there, which suggests that maybe we are really looking at periodic orbit, just evolving slowly in this direction of continuous symmetries. We're back to this original simulation. I'm showing you Rayleigh convection. I'm showing you once again the heat maps with respect to the Wasserstein, the bottleneck. You see velocity of patterns. It really suggests that we're seeing something that's periodic. Again, it suggests that there's time scales. So we connect all those persistence diagrams and ask, is there a circle? Now, that's the persistence diagram you're seeing on the right. I don't really know that those are the right persistence points, because to do this, because of the multiple time scales, we had to take very many time points. And this, I think, is a big bottleneck that needs to be dealt with. Huge point clouds, how to compute persistence diagram with respect to these clouds. What we do on the right was a subsampling technique due to Sean Harper. So let me conclude. I'm probably late. Oh, just on. So we're working towards getting results. What are long-term goals that I think are really conceptually realistic? All this showed you was simulation data. These things are able to be applied to experimental data. Of course, there's no way to go back and check that you're looking at the right thing. If it's with experimental data, that's what we're doing numerical data first. But I think we're ready now just to take these ideas and apply them to experimental data. The thing is that when it's experimental data, we're using these same techniques. What we can do now is start looking at statistics, or in a very general way. So one of the things we want to do is to understand attractors for the experimental data, for the corresponding numerical data, and see if on a crude level the geometry of the attractors match or are comparable. That's not the idea if you think about something like the Lorentz attractor. If you're in dynamical systems, if somebody shows you a Lorentz attractor, you recognize it as a Lorentz attractor because of the very distinct geometric feature. And so as a very crude way of measuring these complex systems, I think that trying to understand the geometry as measured via system homology makes sense as a way to compare very complicated time series data. Another thing, and this is further down the road, but I'd really like to be able to characterize the complex dynamics on the attractors, have a point cloud, and as I said at the beginning of my talk, we have experience. If you have point clouds and you understand how points are getting mapped to points, then in principle, one can get finer descriptions of dynamics. What is that's really driving the complex dynamics? So I think something that's suitable. There's still a lot of technical work that needs to be done before we can get there, but that's what the long goal is. So thank you very much, and I'd like to very much emphasize that this is joint work with a variety of people, both here at Rutgers and Georgia Tech, Virginia Tech, and New Jersey Institute of Technology. Comment. It's floating by as people shuffle their papers, but
I have a question regarding the microdynamic simulation, where you showed there seems to be a phase transition in terms of distance.
And again, let's go back to the
dynamics.
molecular. Oh, this one here. Yes, yes, there is actually.
Yes. The question would be: it seems like this phase transition is very sort of limited through distance computation.
Yes.
I were just thinking about the naive simulation itself. When the different particles were kind of compressed, there feels like there is going to be a drastic drop in both beta 0 and beta 1 when the particles are being closer and closer to each other. I'm wondering if this phase transitions are also very clear from directly computing of the rank of the numbers.
Probably. Thought about that, but I would think so. Yeah. Yeah. My guess is that's correct, but I haven't done it.
So is what do you think is the advantage in computing sort of those distance the signals through distances versus through Betty numbers directly?
Oh, wait. No. I'm sorry. I misunderstood your question. No, the loops. So, okay, sorry. What to remember is that these are disks, all right, and reasonably hard disks. So when you put these disks together, right? You put disks together, and I don't have 3 disks handy. Put 3 together, there's a hole in them. So, and that's a kind of a crystalline structure. If you don't have uniformly sized particles, then you'll get a rather structure. So there's lots and lots of holes that still remain. So you have one connected component for the part. There are disks that get trapped around other disks and just can sit there. You do get a lot of holes that never disappear. Does that make what I just said?
There has to be a drastic drop in sort of high persistent holes, right? For example, a population of disks are moving towards each other. At some point, when they start touching, of course, then the persistence sort of 0 and between 1 doesn't change as much. But then before they got there, there has to be.
You're constantly pushing on this thing, right? So the forces are going up. An actual, landscape of force that you have on these particles, which is what we're measuring, actually dependent upon the types of particles you have in this your collection of particles, uniformly sized or non-uniformly sized, what kind of friction do the particles exhibit?
Oh, okay. So basically, that in some sense that distance measure somehow capture some of those information. Measure changes.
We have shown that in a recent paper, which it's on the archive. So this is with Lou Kondik and Miro Kramer. I should have put that on the slide with and Arnaud Gouillet. So we actually show that these kinds of things can measure differences between this type of systems that you have. Sure. Yes.
For this really nice heat maps from the time series, I think really hard convection, and then you turn that into a persist diagram, and then you calculated the pairwise distances.
Yes.
So that a distance matrix. The heat map was just utilizing a distance matrix. Projecting that, so that's the finite metric space, like projecting that down into 3 dimensions. And
Miro's been doing a lot of this.
Anything interesting you can just see visualizing that?
Yes, we've been actually using Koifman's diffusion map techniques. It seems to be a very nice way to organize. I think in a high-dimensional space, I'm not sure that just I have to figure out, and of course, it's not a very nice space. Your landscapes make it a little bit nicer because you're in an LP space, right? And so, what projections you would want to take, but these diffusion maps that Koifman has are really nice for data and trying to look for geometric structures in them. So we've been
something like a map which tries to preserve like local distances might.
Right. Okay, so I'm not an expert on all these kinds of techniques. I think isomap fits into that diffusion map framework, but I might be wrong. All right. So yes, isomap. There are kernel methods, right? That different properties, one or the other, and how many of them fall into the same tricks and how many are really distinct. That's not my expertise, but I think those are really useful because we do have this point cloud in the metric space, and I think there's a can be exploited there.
Thank you.
Anyone? Well, address if they have a question. All right.
All right. Thanks again, Konstantin.